equation. And the change in boiling point or the freezing point depends on the molality, the concentration of the solution. Okay, so this is another conclusion that we want you to remember there. When you have a non-volatile solute added to the solvent, and the key word there is non-volatile, and if you have, say, alcohol mixed with water there, when you start heating the solution there, alcohol will evaporate, and you end up with pure water in that case. Okay, so if you have salt or sugar, those are the non-volatile solute. When you put them in there, the solution will have a higher boiling point compared to pure water. It's going to be slightly above 100 degrees Celsius, and depending on how much you add in there, you can calculate, you can actually quantify the changes there. How do we do the quantification there? The change in boiling point or the change in freezing point is directly proportional to the molality of the solution. Now, Kb or Kf, and those are what we call the freezing point or boiling point constant for pure solvent. Different solvents will have a different constant, so we're going to give you these numbers here. Now, if you want to figure out how much change, you will have to, the example that I did with the water for my chicken in winter days there. I know the temperature is going to be -8 degrees Celsius, and that's the lowest temperature forecasted there. Now, the freezing point of pure water is 0 degrees Celsius. So the change would be 8 degrees, -8 from the temperature going from 0 degree to -8. The net change is 8 degrees Celsius. 8 degrees Celsius equals to Kf, and the freezing point constant for water, times the molality. If you know the volume of the water, you can convert it into mass there. And then you can figure out how many moles of salt that you have to dissolve in there. Well, if you know the number of moles, you know NaCl, you know the molar mass, and you can figure out how many grams you're going to put in. Okay, so these are the two equations that we can use to quantify the changes in temperature there. And in terms of the constant there, and again, Kf, and that's the freezing point constant, and Kb, that's the boiling point constant. Okay, and these are the numbers there. Okay, so for benzene, for carbon tetrachloride, for chloroform, for water, each has a different value there. And if we ask you to do calculation, and I know when you do Chem 102, and you will see this type of question on the ACS exam here, we will give you these constants there. You just need to know how to define molality, and you need to know that equation for the calculation. Okay, so there's no point to memorize all these equations, all these constants there will be given to you. And using these two equations there, we will be able to calculate the boiling point elevation or the freezing point depression. And we can also figure out the molality of the solution. We can also figure out the molar concentration, the molar mass of the salt, of the solute that we put in there. We'll give you some examples there. So this is the first example. Erythritol is a compound that occurs naturally in algae, and actually it's sweeter than the sucrose that we use there. So we can use that as a substitute for the sugar. It doesn't have as much calorie, but it tastes sweet. Okay. So in this case, we don't know, if we don't know the formula of this compound there, and then there's no way that we can figure out the molar mass of this compound. However, if you prepare a solution with water using this particular compound there, you can measure the freezing point of the solution. So in this case, if you dissolve 2.5 grams of this compound in 50 grams of water, you end up with the solution with a freezing point of -0.762. And we can ask you, we will be able to calculate the molar mass of this particular compound. So how do we go with this particular calculation? Now, the relationship here is that delta Tf, that's the freezing point change between the pure solvent and the solution, water and the solution with this compound there, equals to Kf times the molality, small m for molality. Okay, so this number here, we know the solution freezes at -0.762 degrees Celsius. So pure water freezes at 0 degree. This solution freezes at -0.762. So the difference is 0 minus -0.762. So here, this number will be 0.762. Now, that's in Celsius. Okay, now this number here though equals to Kf. Kf of water, 1.86, times the molality. Now the molality is mass over molar mass divided by the kilogram of water in the solvent. Okay, we know the mass of the compound. We have 2.5 gram in there. Okay, we don't know the molar mass. So we plug in the gram 2.50 gram. And here we have 50 grams of water. We convert it into kilogram, 0.050 kilogram of water. And if you look at this equation there, everything of one quantity is given. So this is what we're looking for. The molar mass can be determined in this case. If you do the calculation correctly, 122 grams per mole. So this is one of the applications there. Actually, prior to, well, way back a couple of years ago, we were actually doing an experiment in the laboratory there, asking you to figure out the molar mass of an unknown compound by measuring the freezing point of pressure, which is a neat an experiment that we can do. We give you an unknown compound. We ask you to measure the freezing point of pure cyclohexane. You put the compound in there, dissolve it, measure the freezing point of the solution again, and you will be able to figure out the change in freezing temperature. And then Kf of cyclohexane is given to you based on the molality. Well, you can figure out the mass of the solvent, cyclohexane, that you use, and you know the mass of the sample you put in there. The molar mass is the only unknown. So this is one type of calculation. And again, when you plug in the numbers there, and you just need to know the definition. How do we define molality? And if you know the definition, then solving this kind of question is really not that difficult. We've been working on more complex calculations than this, and so plug in the number, you get the unknown. Okay. Another type of questions here is we can ask you, if you dissolve 29.3 gram of sodium chloride table salt in 500 milliliter or 500 gram of water, what is going to be the boiling point of this new solution? We know the boiling point is elevated. Okay, so the constant for water, boiling point constant for water is 0.512 degree per mole. Okay, so we ask you, what's the new boiling point of the solution? Well, we know the temperature. We are trying, in this case, we will be able to figure out the change in temperature in terms of the boiling point based on the information given here. So, and delta T B, the boiling point temperature change, equals to Kb times the molality. Okay, so Kb is a constant given there, and that's 0.512 times the molality. Well, how do we define molality? Moles of solute per kilogram of solvent. Well, we have 500 grams of water there, so that's 0.500 kilogram of water. Okay, and then moles of solute, we have grams there, 29.3 of sodium chloride. Each mole is 58 point something, 0.5 grams. Okay, so here, through this particular calculation, you can see gram and gram cancels out, and you get moles per kilogram. Okay, so you end up with the change in temperature, and this will equal to 0.512. So the change in boiling point of this solution is going to be 0.512. What is the boiling point for pure water? 100 degrees. So the new boiling point of the solution would be 100.512. You add 100 to add this change to the boiling point of pure water, 100 degrees there. So the answer